So what had been so radical and, that Bob and Tony caught hell for years has caught on to be very much mainstream science, and it's important science to keep listening to, as we'll hear today, as Bob talks about the ways in which shale gas, I hope I'm not giving anything much away, but to say that, answering your question, that shale gas is in fact a major driver of global warming. So with that as an introduction, here I give you Bob Howarth.
Thank you, Irene, for that introduction. Thank you to the organizers for inviting me today, and thanks to all of you for coming. It's a true honor to speak to this audience. A reasonably small audience, but a lot of important people here and important community. I'm proud to be part of that. I just want to add one slight correction to what Irene said, and that is that Tony and Graffy and I did stick our necks out a while ago, back in 2011, and we certainly got a lot of pushback from the scientific community, although I think, as Irene said, our findings have held up quite well. We'll go through that. My talk today is pretty heavy science-based. But from the start, we also had a lot of support from scientific peers. From the very start, I would go to national and international meetings, and old friends and colleagues and people I hadn't seen in 20 years would come up and give me a hug and thank us for the work. So it's actually, there's a global community of scientists behind this as well, which I want to acknowledge. So my talk today should be about 45 minutes, and then we have time for question and answers if people want. I'm going to go through a fair amount of technical science, and my reason for doing that is that I want you and anyone who watches this on video, because it's being recorded, to know that there is a lot of detailed science behind what we're saying. We're not simply blowing smoke here. And since it's being recorded, from past experience, when my talks that are recorded are posted online, people hired by the oil and gas industry go in and nitpick them to death and post things like that. So I will tell you, I'm being extraordinarily careful. Everything I say today, I can back up in great detail. So if I go into a little bit of detail there, it's not to bore you, it's that I want you to understand that there is very rigorous science here. So my context, we started working on this 10 plus years ago, Tony and I, but I really reinvigorated my eagerness to work on it 4 years ago. I was lucky enough to be one of the people at the COP 21 in Paris. And while we're there, the nations of the world came together and they really agreed that we need to do something about climate change. Of course, they haven't acted on it yet, but they made that agreement. The agreement is still there. And they explicitly recognized that as we blow through 1.5 degrees Celsius above the pre-industrial baseline, the world is facing serious problems. And if we hit 2 degrees, we're in a lot of trouble. The nations all agreed to that. So they said we need to keep the planet well below 2 degrees Celsius. For context, we're at 1.1 degree right now. We're on target to hit 1.5 in about 9 or 10 years from now. This is not some far off target. I'll show you some data on that in a minute. And the take-home message is that if we want to reach that target and keep the planet well below 2 degrees Celsius, we have got to reduce methane emissions. Absolutely must. So I want to distinguish between carbon dioxide and methane. They're both carbon gases. They're both critically important greenhouse gases. They are the two most important greenhouse gases, but they're fundamentally different. For carbon dioxide, once we put it into the atmosphere, it'll be with us for centuries, probably 1,000, maybe 2,000 years to come. But the climate responds slowly to it. About a quarter of the carbon dioxide from fossil fuels is taken up by the ocean on the time scale of 500 to 1,000 years. A lot of it's also taken up by forests, and that's re-released, so there's a buffering in the time response of the climate to carbon dioxide. If we reduce carbon dioxide emissions now, we have to, but the climate will respond slowly to that. If we look at methane, it's fundamentally different. There's a lot less methane in the atmosphere, but it's a far more powerful greenhouse gas, more than 100 times more powerful. And it's only in the atmosphere the half-life of about 12 years. It's then oxidized to carbon dioxide and water, but it's gone as methane. And so it's critically important, but over a much different time frame, and that'll come back throughout the talk, how we think about that how we manage our greenhouse gas emissions, how we think about it. So this slide is from the IPCC, the Intergovernmental Panel on Climate Change, from their 2013, the last major synthesis report. And what I'm showing you there at the top is the radiative forcing for carbon dioxide and methane and then other greenhouse gases. So you can see that this is the cumulative warming that these gases have caused the planet over time. That's what that shows. For carbon dioxide, it's the most important. It's 1.66 watts per square meter of heat absorbing that's occurred. Methane's not far behind, though. It's 1 watt per square meter. And the other greenhouse gases are important, but nowhere near as important. Now, I love this figure. It was published by Drew Shindell and others way back in 2012, but it's as valid now as it was then. And what it shows is the rate of atmospheric warming over the 20th century up to 2011. So that squiggly line is the warming that's occurred. And of course, we saw an acceleration over the last couple of decades, and that continues to accelerate. And then we're seeing projections into the future, again, going back from 2012, because that's when the paper was published. And the first line there on the top, the green line that says reference, that is what the projection would be if we made no effort to reduce our greenhouse gas emissions and we just had the status quo continue. If you see, we blow through 1.5 degrees in about 10 years from now, and we blow through 2 degrees C in about 25 years from now under that scenario. Turns out we've actually increased our greenhouse gas emissions more than that scenario, so we're warming faster than that, which is a bad scenario. The next line down where it says CO2 measures, you can see no effect for a while. That's what would happen had we back in 2012 aggressively started to reduce carbon dioxide emissions. And we need to do so because of the long-term influence of carbon dioxide 1,000 years out. But it does nothing over the time frame in the next 20 to 25 years. The Earth continues to warm, and you can see only 20 to 25 years into the future does it slow down from reductions which would have started in 2012. So carbon dioxide alone will not keep us well below 2 degrees C. It's just not possible. The bottom two lines are what happens if we reduce methane emissions, if we'd started back in 2012 to reduce methane, and in one case also carbon dioxide. And again, the climate responds very quickly. So the only way that we're going to reach that COP21 target and keep the planet well below 2 degrees C is to reduce methane emissions. That's the context. So another context is this idea, which I'm glad to say is everyone in the world now thinks is outdated, but this idea that natural gas might be a bridge fuel. And this was wildly promoted, as many of you know, by the natural gas industry, say 5 years ago, certainly 10 to 15 years ago, and it was picked up by President Obama and his administration, unfortunately, too. They were believers in this idea. And the data supporting the idea is shown here. What you're seeing is the amount of carbon dioxide emitted from the same amount of energy produced for various fuels. And when we burn natural gas, it produces less carbon dioxide than coal and less than diesel oil. And so the thought is we can't simply move to the renewable future. It's too difficult. We're stuck with fossil fuels. Let's get rid of dirty coal and substitute clean natural gas. That's the thought, less carbon dioxide emissions. The problem with that, and this is widely believed, promoted, talked about by Obama in his State of the Union messages more than 3 times as a focal point, and it was all happening about the same time as the shale gas revolution started, which I'll get to in a moment. But the problem with the argument is it ignores methane, and methane, natural gas is mostly methane. 90 to 95% of natural gas is methane, and again, methane is a much more powerful gas. So if you emit a small amount of unburned methane to the atmosphere, it undoes whatever climate good you could have from carbon dioxide. The whole idea of the bridge fuel is now moot because all climate scientists agree we need to get rid of all fossil fuels as quickly as possible. There is no room for any. And furthermore, we now have the technology that's cost affordable to have a renewable transition. We don't need fossil fuels. So the idea is dead, but it's still there as a background context. So the shale gas revolution. Shale gas is what I'm talking about today. And is there anyone in the room who doesn't know what shale gas is? I don't need to explain what shale gas is, right? The technologies for developing shale only came about in the 20th century, and they're high-precision directional drilling combined with high-volume hydraulic fracturing, or fracking. So we had virtually no shale gas development until the start of this century, and it's exploded since. The figure there on the lower right shows you the production up through 2018 of various shale gas plays in the United States. Conventional gas has gone down. And right through until a few years ago, virtually all of the shale gas production in the world was in North America, mostly in the United States. I'll come back and talk about that later. We're getting a little bit more now in China, a little bit in Argentina, but still largely a United States phenomenon. So I really was not paying attention when fracking and shale gas first started, say in 2006 or 7. It was 2009 before I woke up and go, this is amazing, something's going on. And at the same time, the bridge fuel idea of natural gas was being promoted. And I've worked off and on methane since the 1970s, so I was immediately concerned that maybe people are missing the boat here and we should be looking at methane. So I started in 2009 thinking about this, see who else was worried about methane from shale gas development, and where the papers were, where the literature, where the analyses were, and there weren't any, and there was no one working on it. It quickly became apparent. And I didn't know much about the technology of shale gas. My background is in earth system science, and I know a lot about methane and climate change, but I'm not an engineer. I don't know much about, well, know more now than I used to, but I did not know much about shale gas engineering. So Tony Ingraffi and I found one another. He's an engineer who, of course, knows the engineering, and we worked together with Renee Santoro. And we published our first paper back in 2011, the very first peer-reviewed analysis of the role of methane from shale gas development as it might be a climate driver. And I'm showing you where it came out there fairly early on in the process. And coincidentally, there was a big decrease in shale gas development at the time our paper was published. I think that's coincidence. I don't think industry was responding to us. But it picked up again very soon after that. And this is a figure from our paper, and I'm not going to go through any detail. I just want to point out, a couple of things here. We looked at the greenhouse gas footprint of a bunch of different fuels, conventional gas, shale gas, coal, oil. And the bluish color there are the direct carbon dioxide emissions when you burn the fuel, and that hideous magenta color is methane converted to carbon dioxide equivalents from our best estimate of what the emissions might be like. And we put in two plots because the time frame over which you compare carbon dioxide and methane is critical, and I'll come back and talk about that later. It's still subject to a lot of debate. We used two different time frames because the science which I had thought was most respected over the previous 20 years before that had done so as well. But we've gotten a lot of criticism. There are a lot of people who say you got to look at the 100-year time period, which is absolutely wrong. And one of our conclusions was, we didn't make measurements. We went into the, I was going to say literature, but there really wasn't any literature. So what we were doing was looking for data from which we could estimate emissions, and these are from EPA websites and industry websites and from industry sources. Tony and I started giving public talks about this stuff in 2010, and the press picked up on it right away. So New York Times was talking about our talks back in 2010, a year before our paper came out. And interestingly enough, people in the industry started leaking us stuff, saying it's worse than what you're saying in your talks. And to the extent that we could verify what had been leaked to us, we used it in our report. So it's a mixture of leaked material and unpublished stuff from EPA that we had, but not a lot of reliable, easily checked data. So it was speculative, and we said, people really need to go out and do a better job of doing this. And I'm delighted to tell you that in the 8.5 years since our paper came out, ours was the first study, there are now somewhere in the neighborhood of 1,400 papers published on this, and perhaps 250 of those have new primary data. So it's been a huge explosion, and Tony and I and others try to keep up on this. It's a hard job, but I'm going to try and tell you today what the latest from that is. Going back a little bit in time, the sort of studies which were done, this is one of the few field-based papers that I'm a co-author on. So this was published back in 2014. Dana Carlton was a graduate student at the time. And they flew an airplane equipped to measure methane in real time up and down in southwestern Pennsylvania over the Marcellus shale field there, and mapped basically distributions of methane in the atmosphere. And from that and the meteorology of the time, we could estimate what the methane fluxes to the atmosphere were. And our take-home conclusion was that the fluxes on the day or so that we're out there measuring were greater than what Tony and I had predicted in our original paper. And there were some surprises, and I'll just give you one surprise, and that is that we found several wells which were being drilled, which were emitting large amounts of methane to the atmosphere. They had not yet even hit the shale. They had not been fracked. They were not in production. So during the drilling phase, there was a lot of emissions. EPA still doesn't recognize that, but it's a fact, and it makes sense because the Marcellus Shale is fairly deep in the ground, and there's a big history of energy development in the area, coal, oil, and gas going back 150 years. There's a lot of history, a lot of methane trapped in various things, and when you drill through that, you release it. Another study, one of my favorite ones, this is a satellite study published back in 2014, Oliver Schneising and colleagues, and they looked at the global distribution of methane over time using satellite, which you can do because methane is such a powerful infrared absorber. That's why it's a greenhouse gas. And they said that some of the shale gas fields were emitting huge amounts of methane. So I published a review paper back in 2015, just over 4 years ago now, trying to summarize all of that. And here are the data from that. We're looking at the percent of the natural gas produced in shale gas wells over time that's emitted to the atmosphere. In this case, we're looking at what we call the upstream emissions, so those that occur at the well site or in the gas fields, and they're listed chronologically. So at the top is the estimate that Tony and Renee and I published. Again, it's a percent of the lifetime production of a well. Right below that are some estimates of EPA, and I won't go into detail there. They took our results for a while and then decided not to, is the bottom line, so they retracted. And then each of those blue lines is an individual study. Some of them are higher than others. The two of the highest, they are not the very highest, but the two highest ones are the ones I just showed you, the satellite data and the airplane flyover, but there are a lot of lower ones. And I think most of these are pretty reliable studies, data. The one that's in orange is not, in my mind, it's been discredited, but most of these are good data, so what you see is a lot of variability in space and time, which makes it hard to synthesize and pull it together, but people are trying. So the latest synthesis of which I'm aware is this, which was published 3 months ago by Wren et al., and they pulled together not all of the studies, but what they thought were the most comprehensive studies, again, looking at the methane emissions at well sites and so producing facilities. They're not looking at the gas pipelines, et cetera. And that's hard to read. Let me just point out that I think they did a really good job. I'm going to criticize them here, but it's not because they didn't try. It's difficult to pull this stuff together because everyone uses different units, different terminologies, and it's very confusing. But let me just tell you that I think they got a couple of the numbers wrong. So I've corrected them, and I know some of these are wrong because there are published papers, and they simply misinterpreted what we had said. But what you're looking at here is from top to bottom, the highest estimates at the top, the lowest at the bottom. The orange line there at the bottom is the study, which I don't believe. It's been discredited quite firmly in my mind. But what you see is quite a range of values. The two blue ones there I've corrected, the 2.2% and the 1.9%. The 2.2 is out of our original paper from 2011. And the 1.9 is the most recent compilation from the Environmental Defense Fund. And I hear all of the time from people in the press that our numbers are so much different from the Environmental Defense Fund. What's going on? Well, they're not. It's 2.2 versus 1.9. And theirs is based on a huge amount more data than we had, but the bottom line is with a huge amount more data, our original story is holding up pretty well. So I'm going to try and pull together these data with a few others and give you an update of what I think the best estimate is at the moment. And let me just tell you that the environmental defense study there, Alvarez et al. Published about 1.5 years ago. They have a ton of studies behind that. The Environmental Defense Fund, working with industry, has put about $100 million into dozens and dozens of field studies. Most of them, I think, are pretty good, and their summary says it's about 1.9. Now, one thing to keep in mind is that these are all sort of ground-based field measurements, and they also looked at things like the airplane flyover I talked about. And what we see systematically is when you do airplane flyovers or look at sort of regional scale, you get higher numbers than you do when you measure things on the ground. And I could go into why that's true. There are a lot of reasons it's true. I'm going to correct their number in just a minute for the difference between the sort of top-down airplane approach and the bottom-up facility scale. But I just want to tell you that the Environmental Defense Fund actually agrees with what I'm saying here. Again, so this is from a press report that came out last month in Europe. It's quoting Stefan Schwitzky, who works for the Environmental Defense Fund and has done a lot of the other global methane work, and he points out that the studies such as EDF has done have an inherently low bias. You can't measure what you don't expect to happen, and that's always going to give you a low bias. One other study I want to mention, because those are all upstream what's happening at the well site, but of course we lose methane all the way through to final customers, pipelines and distribution systems, et cetera, and there's been a lot less study on that, but there's this really nice study that was published last summer by Plant et al., and they took airplanes and flew them up and down the east coast of the US between Washington, D.C. and Boston on several occasions, and they were able to estimate the regional scale methane emissions from that particular area, and they're able to backtrack how much of that might come from wastewater treatment plants and landfills, et cetera, and how much of it's from the oil and gas industry. And the bottom line is that they are saying a little bit less than 1% of the natural gas that's consumed or produced is being emitted in these final distribution systems. That's a pretty big number. All right, let me put that together for you and give you what I think is the best estimate as of the moment from what natural gas emissions are in the United States as of 2015. And so we have what's going on at the well site, what I'm calling production, processing, gathering, et cetera, and also including the high-pressure transmission pipelines. And that's from the Environmental Defense Fund number, but correcting for the top-down estimates, it's about 2.6% of the lifetime production of a well. And the next number is what's going on in storage and the local distribution, and that's 0.8% or so. So 3.4%, very conservatively, is being emitted to the atmosphere. And by the way, that's exactly the mean estimate that Tony and I published back in 2011. Now, I think it's conservative. Why do I think it's conservative? Well, the studies I'm showing you there with the red arrows are the two I just mentioned, the Colton et al. Airplane flyover and the Schneising et al. Satellite data. Those are some of the higher top-down estimates, and the Environmental Defense Fund ignored those. So they have a bias. They also ignored the fact that there are emissions during the drilling, as we showed in Colton et al. So the 3.4 number it's a good estimate, but it's conservative. There is no way you can play with these numbers and get an estimate that's lower than 3%, but you can easily increase that up to about 6%. So the reasonable range of estimate is 3 to 6%. 3.4 is a conservative, low, but highly defensible number. And I have a paper in review where I'm trying to use that, so I've tried pretty hard to get something that's defensible and extrapolable. So let's look at what's going on in methane globally, and I'll come back to that number in a minute. This is the global average atmospheric concentration of methane from 1980 up to 2015. And you see it was rising pretty rapidly in the late 20th century. It actually flattened off, and the emissions stabilized in 2000 or so, and for a decade they were flat, no increase in emissions. But they've been going up again since about 2008 or so at a pretty rapid rate. And again, we want to reduce methane emissions if we're going to reach that COP21 target. So it's the wrong direction, and we need to understand what's driving that. And there's been a huge amount of interest in the scientific community as to what's driving it. I think it's, in large part, I think it's mostly fossil fuels, so there are other contributors. I think shale gas is a major player, and I'll try to convince you of that. And you're probably convinced already, but I'll try to convince others of that. And for context, again, this rapid rise in methane happened about the time that the shale gas revolution started. And 63% of the total increase in natural gas production globally from the period of 2005 to 2015 is shale gas development in the United States. The United States is now the largest natural gas producer in the world. We were not back in 2005. So it should not really be a surprise when you change the technology that much, increase production that much, that would have a global influence. Does it? Well, here's the calculation I would use. We have estimates of what global shale production was. It was 31 billion cubic meters back in 2005, and by 2015 it was 435 billion cubic meters. If we use that number that I just gave you, that 3.4% of this is emitted to the atmosphere as unburned methane over time, and we assume that 93% of shale gas is methane, then we say that back in 2005, 0.7 teragrams of methane per year were being emitted from shale gas development and use, but by 2015 that had increased 14-fold to 9.2. What's a teragram? It's a trillion grams, so 10 to the 12th grams. And this is for all shale gas globally, but 99% of that over that time period was from North America, and 89% of it was from the United States. If we put that in context, the difference between 0.7 and 9.2 is 8.5 teragrams per year, so that's the increase in emissions. Again, conservatively estimated, it might be up to 75% greater than that. That is 34% of the total increase in global methane emissions over that time period. So I believe at least a third of the global increase is coming from shale gas. And there's other evidence I'll show you, and again, for that in a moment. So that's the time period we're talking about. That's the increase. At least a third of that is coming from North American shale gas development. Well, what about cows? Because you hear a lot that cows, agriculture is the real driver. It's all over the place in the press. There are two reasons for that. One is the oil and gas industry works very hard to get people to think about cows. And the other is that there were two highly influential papers published back in 2016 saying it probably was biogenic sources, probably cows, that are driving the recent increase, not oil and gas. So the first of these was published by Schaefer et al., came out in March of 2016, and they said 84% of that global increase over the last decade is from biogenic sources, probably mostly animal agriculture, and they said right in their paper that this is surprising given what's going on with shale gas development in the United States, but nonetheless, that's what their data showed. And there's another paper that Schwitzky et al. Came out in Nature later that year, November of 2016, said sort of the same thing, different data. I'll show you a little bit of the data in a minute. It's an interesting story, and it's really compelling at one level, but I don't think it's right. So the basis is based on the isotopic chemistry of methane. And how many of you remember high school chemistry? A couple of you. You know, methane is a carbon atom with 4 hydrogens around it, and there are different isotopes of carbon. So most of the carbon on Earth is carbon-12, but some of it's a little bit slightly heavier carbon, carbon-13. And you can measure the change in the carbon isotopic composition of methane over time, and that's what this data shows. So the top is what's going on. I've shown you that already. It's the change in atmospheric methane over the last many years. On the bottom is what's going on with the isotopic chemistry of that methane on average. So in the 20th century, as the methane was rising, it was also getting more enriched in the heavier isotope, carbon-13. For the first decade of this century, when the concentration was constant, the isotopic concentration stayed the same. And then when methane started to rise again over the last decade, the chemistry started to change. It got less carbon-13 as opposed to more carbon-13. And that's the basis for saying it's probably cows. So very, very simply, we're looking here at a measure of what the isotopic composition of methane is. Don't worry too much about the terminology. What I want you to look at is that little triangle in the bottom. That's sort of the balance point of what the average of all sources of methane going to the atmosphere would have been back in 2015. The blue bar is what the isotopic composition of methane coming from cows and wetlands and other biological sources is, and the red is what people thought for fossil fuels. And the bottom line is that the signal has edged ever so slightly to the right on this plot towards that biogenic source. So that's how they're calculating it. And the arrow there is highly exaggerated. It's a much smaller signal than that. Now, there are reasons to be suspicious of that right from the start, and I was suspicious. I mean, the day the paper came out in March 2016, I was getting calls from reporters all over the world saying, how do you make sense of what they're saying? And I can't. It doesn't make any sense to me. It took me a few years to figure out why I couldn't. But the reasons to be skeptical is that we know there are some data, although they're conflicting, on what the spatial distribution of changes and fluxes are. And most of those say the United States is a big player. So let me give you this example, another satellite study published in 2016, and they concluded that over the last decade, 30 to 60% of the entire increase in global methane is coming from the United States. That's quite consistent with what I just told you in shale gas, but it's not in terms of animal agriculture. I'll get to that in a minute. The Guardian picked up on that and said, yeah, it's the U.S. is the cause of this. I already mentioned the Schneising et al. Study. They also used a different satellite, and here you're looking at over time. The redder colors are the increase in methane 2003 to 2012, and you see a bigger increase in the northern hemisphere. So the satellite data were telling us a lot of the methane is coming from the United States. Most of it's coming from the northern hemisphere. And the problem with that is that if biogenic sources of cows are the problem, cow numbers were going down in the United States over that time. They've been going down for quite a while. And globally, cow numbers are flat. And there's no reason whatsoever to think that there's been an increase in biogenic sources, methane from cows. I will add that the spatial, the people who study the spatial stuff argue a lot. The satellite data showed what I just stated, but there's also monitoring data which you can pull together in simple models, and this paper by Nisbet et al. Say, no, there's actually a big increase in methane in the southern hemisphere and the tropics. That's more consistent with perhaps wetlands, so there's a debate about that. And we will know in another 4 or 5 years what's really going on. The satellites are a really powerful tool. 2 satellites I showed you both went out of commission in 2012. So we've had no data for the last 6 or 7 years, but the European Space Agencies has put up new satellites which have been collecting data for the last year, and they're much, much better data. And so we will soon be able to look much more precisely at what's going on. All right. I was skeptical of the study. They were saying it was cows. Didn't make sense, but I couldn't really put my finger on what was wrong. And the first paper which really clarified it for me was this one, which came out in November of 2017, just over 2 years ago. And if you look at the title there, they're reconciling the conflicting estimates. What they're saying is the spatial data don't agree with what these people have said on isotopic composition. Why? And they make a very simple case that the 2 high visibility papers from 2016 blew it because they missed a change in one of the big sources. And trying to constrain global budgets based on this isotopic chemistry with multiple sources is really challenging. There's a lot of uncertainty in it. What these guys pointed out is that the biomass burning globally, which is another source of methane, actually decreased over the last decade. And although biomass burning isn't a huge source of methane, it has a very, very distinct chemical signal in this carbon-13. It's way over there to the right. It's really heavy. So what I'm showing you here is a reevaluation from the Warden et al. Paper. If you allow for the fact that the biomass burning went down, there's less pull that way, if you like, and if you ignored that, you were misinterpreting and over saying there's more biogenic than there is. So this is a reinterpretation of it. The reinterpretation is that there's more emissions over the last decade increasing from fossil fuels in that reinterpretation. And this is a little busy, and if you're tired of science, close your eyes for a minute. I'll wake you up again in a minute, but I want to just show you. This is out of that paper, and what we're looking at is on the top is the increase in fossil fuel emissions, various estimates, and the bottom, the increase in agricultural cow emissions, basically. And there are 2 different colors on there. So the blue is that original March 2015 paper, and the red is the newer data that came out later that year in Nature, where there's no biomass change. Both of those studies are different because of the quality of the data, but they're both saying that the emissions are higher from cows than from fossil fuels. When you correct on the right and say, no, there's a change in the biomass source, then you qualitatively change that. The fossil fuel estimates shoot way up. And the best estimates there are the red ones, best data sets, and including biomass. So for those of you who follow it closely, this was called a NASA study. People say NASA proved back in 2017 that really it's fossil fuels. This is the study which did that. So my contribution, I published a paper this past summer, and I took a slightly different look. I built on that paper I just described, but I added onto it. And my thought was that shale gas might be different than other fossil fuels in terms of its methane. And the reason I thought about that was that if we look at conventional natural gas, this is highly cartoonish, but in the upper corner there, conventional gas is methane that is migrated from a source rock, such as a shale formation, over geological time frame, tens, hundreds of millions of years, until it gets trapped under a cap of some sort, and that's what conventional gas is. The methane, which is left down there in the shale, is what shale gas is. Well, when the gas migrates, somewhere between a third to three-quarters of it is either chemically oxidized or oxidized by bacteria. And when you have a chemical reaction, you have fractionation. The bacteria and the chemistry favor the lighter carbon-12 isotope. They leave the heavier carbon isotope preferentially more behind. So the methane, which ends up in the conventional gas, has more carbon-13 in it than started out in the shale gas. We would expect shale gas to look different in terms of its methane than the conventional gas. And I just said all of that. So my paper just reinterpreted the global models which were published, taking into account that shale gas, it's not hugely different, but it's a little bit different. So the plot on the upper left there I already showed you. It's from that Warden et al. Paper. Here's my reinterpretation. Again, with the balancing, the shale gas has a little bit less carbon-13, it's a little bit more in that direction. And when you throw that in and separate it out from other fossil fuels, you end up decreasing the biogenic sources more, and the sum of the shale gas and other fossil fuels increases. And if I put it on the plot I just showed you, the stars are my new estimates. This explicit inclusion of shale gas methane doesn't hugely change the conclusion from the NASA study. It increases the fossil fuel sources some, it decreases the biogenic sources some, but they're not huge differences. What is more important is that it explicitly says that a large part of that fossil fuel is coming from shale gas from North America, a large part of the United States. So what my reinterpretation does is tell you which fossil fuel and where, because it is shale gas for a large part, and that's North America. So if we take my paper there and the estimate of how much methane is emitted from the shale gas, ignoring everything I said before, this is calculated just from this global budget and the global change in that isotopic chemistry, I conclude that 3.5 to 4% of the lifetime production of shale gas is going into the atmosphere, and 2.8 to 3.5, and I can't better constrain the difference, but about 3.5% of shale gas and conventional gas, and compare that with the 3.4 number I gave you before, which is derived from totally independent data. There's nothing in common with these calculations. So I really believe that about 3.5% of the methane from shale gas is gone to the atmosphere. I think it's hard to argue with that. And if we put that into a global context, this is the global budget of methane from all sources. The black and blue numbers are from 1995, and this is out of my textbook that was published back in 2014, just updated a little bit. The red numbers are updated with what we now know has changed in methane. So there are a lot of natural sources, mostly wetlands and lakes, but their human sources are larger. We've grown that by about 25 teragrams over the last decade. It's all human sources, it's not a natural increase. And natural gas and oil are the single biggest cause of that. A little bit from coal, some from animals as well, but it's mostly natural gas and oil, and shale gas is the major player in that. Okay, that's a lot of science. Let me just entertain you here for a minute, and then we'll get a little bit back into science. I just want to remind you that when I'm talking about these 3.5% leakages, it isn't all at the site of the production. It's full life cycle all the way to final consumer, and methane leaks each place, and it's hard to measure. It's also hard for people to visualize it because methane is a colorless, invisible gas. So here are two pictures taken by Sharon Wilson. This is a gas separating plant in Texas, and the tank on the left is how it would look to your eye, and you don't see anything, but on the right with a FLIR camera, infrared tuned camera, you can see the cloudy-like stuff. That's not smoke, that's methane. It's leaking out. And we know from the work of Nathaniel Phillips, he drives a car up and down the streets of Boston measuring methane real time, and so that's the grid of Back Bay of Boston, and the yellow there is the methane concentrations. The higher the spike, the higher the concentrations. A lot of methane leaking out over time. Again, you don't see it, but it's there. Now, Irene mentioned the incredibly nice piece in the New York Times from 2 days ago. Actually, it came out. If you haven't seen it, you should go take a look. I'm just going to show you a couple of pictures. This is one of their first. So they went down with Sharon Wilson and others and did this FLIR imagery of lots of fields in New Mexico and Texas and the Permian Basin. And here's a storage tank, and there's the FLIR imagery of it. Again, the stuff that looks like smoke is methane. And this is one of my favorites. So Here's a gas processing facility in Texas, and they ask the question, one of these stacks, they say, is streaming methane. You don't see it. If you haven't seen this yet, take a guess as to which of those stacks is emitting. Everyone have a favorite stack you're looking at? It's that one. You'd never know if you didn't have the FLIR camera. And this stuff is going on all the time, right? Okay. A little bit more on methane, and then I'm going to talk a little bit about the time frame and how we account for it and take us up to what New York State is doing, which I think is pretty cool. I just want to point out that this is the work of Drew Shindell from a lecture he gave here in Ithaca earlier this year. I'm talking about methane as a greenhouse gas, which it is, but that's not the only problem with methane. It does a bunch of other stuff that carbon dioxide does not. It causes ground level ozone, which is just terrible for public health, asthma, et cetera. It's bad for agriculture, it's bad for forestry and all. So when you look at the health costs and the agricultural costs and the environmental costs of methane in addition to climate change, and then put a cost on it relative to carbon dioxide, both of these include the cost of climate change as well. Methane is a hugely expensive pollutant. And if you take my number and say that we've increased the flux of methane by 22 teragrams per year over the last decade, and take that social cost, that's a cost of $600 billion, which is borne by real people on the planet, or $60 billion per year, that increase in methane has cost to society. So I showed you this already, and I want to remind you that methane and carbon dioxide work on fundamentally different time frames, and then we need to think about, therefore, how we compare them when we talk to decision makers and policy people. How do we do it? They're both carbon gases, but they're fundamentally different. And again, this is from Drew Shindell. It shows it in a nice way, sort of a thought experiment. And what he's showing you on the left is an instantaneous pulse, one point in time, of three different radiatively active substances. So the BC, the green there, is soot, black carbon. The methane is red, and the carbon dioxide is blue. And the carbon dioxide stays with us a long time. The soot disappears right away, and the methane has a 12-year half-life. On the right is what that means in terms of global temperature. And the soot, even though it disappears right away, has an influence on climate for 5 to 10 years and decays off. The methane has a pretty large influence, as large as carbon dioxide for the first 10 years or so, and then decays off. But over the time period of 10 to 20 years, it's a big problem for, again, an instantaneous release. So we really need to think about it. If we're concerned about climate change over the next decade or so, and we need to be, we need to worry about methane again. And the reason we're worried about climate change over the next decade, in addition to the fact that we're already seeing damage from climate change, is fundamental tipping points in the climate system. If we warm the planet sufficiently, we will fundamentally change the way the Earth systems operate in a way which might take 10,000 or 100,000 years to come back. And that's fundamentally dangerous experiment for society. So this is out of the IPCC assessment of 2007, and what they're showing, I'm not going to go through these in detail, but there are various things that they were worried about, fundamental changes in the climate system. And the white suggests that we don't need to worry about these too much as long as we don't warm the planet above the temperatures you see there on the left. Red means we're in a lot of trouble, it's high risk, orange is in between. And the one I do want to talk about is the one there on the right, this Atlantic meridional overturning circulation. That's a big word. Oceanographers tend to call this the Great Ocean Conveyor Belt. And it was thought back in 2007 that we needed to warm the planet to 3.5 degrees or so before it was a problem. Well, that's not true. We've already started to change it. And it's now very well known that we've started to change it. And it's because we've been melting Greenland ice and Arctic sea ice, and this is the circulation pattern. If you look at the North Atlantic over there on the far side of the plot, what that's showing you is water, warm surface water is sinking, goes down, becomes blue, deep ocean water. It stays in the deep ocean and circulates over the Indian Ocean and Pacific Ocean and comes back to the surface on a time scale of 500 to 1,000 years, and then that water flows back, and this is the global circulation pattern. What makes it sink there is it's the heaviest, densest water on Earth because it's salty and it's cold. You add fresh water from melting ice in the Arctic and Greenland, and it's less salty, it doesn't sink as fast. It slows the whole global circulation pattern, and that's bad. Washington Post picked up on this a little bit. There are a couple of consequences. It changes the climate immediately, but it also, a quarter of the carbon dioxide from fossil fuel emissions is being taken up by the oceans, and that slows when we slow the circulation pattern, so we get a runaway feedback of climate change as well. And the point I'm trying to make here is that the warming we're doing now, driven in part by methane, can cause fundamental changes in this sort of pattern, which will be with us for 10,000 years. And so it isn't true that we only need to worry about carbon dioxide. We need to worry about all the greenhouse gases that are acting in the shorter term. One other example of a tipping point, this is from the New York Times earlier this week, and it's from the NOAA climate report. They say things are going to hell in the Arctic. This other report, another press report, same article, talks specifically about the melting of the permafrost and what that's doing to greenhouse gas emissions. And the bottom line is that we're seeing an increase in carbon dioxide and methane emissions from melting of permafrost. And a lot of people have been worried about this for quite some time. And what I showed you earlier in my talk, methane's been increasing through 2015 or so. That is not from permafrost. We know that because we could see the monitoring data. Unfortunately, that's no longer true. So what I'm showing you here is the very latest data. It's not published, from NOAA. This is the atmospheric concentration of methane over Point Barrow in northern Alaska. And it's going up and down seasonally over several years, but it's staying fairly low, so we didn't see an increase from permafrost melting. This year, 2019, we've seen the highest spikes ever seen in that place. So this is probably from permafrost melting. And again, that feeds into the climate, and there's a runaway feedback associated with there. Very, very damaging. So the bottom line, we need to be concerned about the short term, not just the long term. And there are many tools which we have for comparing carbon dioxide and methane, but the one that we tend to use and that policymakers understand the best is this thing called the global warming potential, and it's the cumulative influence of warming of methane compared to carbon dioxide over a defined period of time when you release them both as a spike in time. And here are numbers from 3 different IPCC reports over time, and it's a different number at 20 years and 100 years each time. The reason it's lower at 100 years is that the methane's only influencing heating for a time period of 25, 30 years and it's gone. You'll add in another 70, 75 years, it's not doing anything, it just looks like it's diluting the influence. But it's doing a hell of a lot on the shorter time period, and that shows up in the 20-year time period. The reason the numbers are going down and increasing as we come to more recent reports, it's not that the physics of the Earth is changing, it's that our understanding is changing. So the bottom numbers are better numbers, is the bottom line. So what do we use when we do greenhouse gas footprint calculations or inventories? Almost all governments in the world, US government for sure, state of New York for sure, uses the 100-year global warming potential, and they use one of those 2 numbers from outdated science. They don't even use the most recent number. And they used to say that's because the IPCC told them to do that. The IPCC responded to that in 2013 because the paper that Tony and I put out, among other things, started a debate about this. We were using 20 and 100-year time periods, and a lot of people are saying we're wrong. The IPCC said there's no reason for using a 100-year time period. You should use the time period that's appropriate for your question at hand. And again, I would assert, given what's going on the planet and the worry of what happens the next decade or 2, we should be looking at shorter time periods than 100 years. So I and others have been arguing that for quite some time and getting some traction finally. So let me just give you a little bit of an example of that. Again, when you have a greenhouse gas inventory and you throw methane in it, not just carbon dioxide, you need to explicitly look at a couple of things. The time frame is one. And since 1997, most people have used this 100-year global warming potential. So I'll just give you an example of Cornell, of how this plays out, because I'm quite familiar with how we calculate things at Cornell. Cornell gets all the heating and electricity, it's shale gas from Pennsylvania. There's a lot of methane emissions associated with that, but most of the methane emissions occur in Pennsylvania, a little bit in New York, but none of it on Cornell's campus. And the traditional protocol says you don't include it as a problem unless it happens in your space, on your campus. So there's a trivial amount of methane emitted on the campus. But of course, the fact that we're using the gas means that we are causing the emissions in Pennsylvania, right? So I and others have said we need to take not a geographic boundary, but a personal responsibility, if you will, threshold, and account for it in that way. And In 2016, I made that argument to Cornell. I was part of what the provost appointed, this SCLAG group, and we argued, I argued, and they agreed that we should take responsibility for all our methane emissions, no matter where they occur, that we should use a 20-year global warming potential, and that we should use the best peer-reviewed science and not outdated EPA stuff, which is industry influenced. And Cornell did that, and it looks like this in terms of what the 2014 greenhouse gas inventory. On the left is what you look, if you included just carbon dioxide as well as the methane emissions that occur on Cornell's campus using a 100-year time period. And on the right, a big, I don't know what color that is, but that big balloon thing is when you include methane leakage under that time period. Now, it's probably too big. I talked to Cornell into using a bigger number than I would believe now. That's more than 3.6%, so I would shrink that by probably half, but it's still a big footprint. Moving forward, once Cornell did that, we talked Tompkins County into doing it as well. And again, going back to the sort of leadership from this community, once Tompkins County and Cornell did it, we were able to argue to the state that they should do it. And the state did do it. The Climate and Community Protection Act, which Steve Engelbright and Barbara Lifton and others wrote, was passed by the New York State Assembly several years, but it actually specifically included that sort of greenhouse gas accounting in the 2017 and 18 versions. And it is now law under the CLCPA rubric. The governor signed it last summer, and it includes the language from 2017 and 18 on greenhouse gas accounting, which I helped them write. So it's what I just described. And I want to give you one example. Thank you. I want to give you one example of what it looks like when you start looking at a particular issue. Just another slide or two, and I'll be done. And the case I want to make is for how we think about how we heat our hot water in our homes. And I've been arguing for a long time that one of the low-hanging fruits for reducing our greenhouse gas footprint in this state is to put air source heat pumps in our home and get rid of our fossil fuel heaters. So I'm running through the calculations here based on the classic way you might think about it, and then the new greenhouse gas accounting, which will be mandated by the CLCPA, hopefully as of January 1st. So what we're looking at here is the amount of carbon dioxide per hot water that's heated. And I've got two types of hot water heaters over there, natural gas heaters, typical ones in the home, or number 2 fuel oil or propane. They produce more carbon dioxide to get the same amount of heat because natural gas really does produce less carbon dioxide. But over here is what would happen if you used a high-efficiency heat pump instead. And first, I'm showing you if we're using average grid electricity off of New York State. The next one, which is a much smaller number, we were actually very fortunate here that our electricity does not have much fossil component. It's got a lot of hydro and a lot of nuclear, but not much fossil. So for the average in this area, that's what the greenhouse gas footprint would be in terms of carbon dioxide. And of course, if you had 100% renewable, it's virtually nil. But if we throw in methane to the accounting, using, again, the full life cycle, even if the methane's occurring in Pennsylvania in the 20-year time period, et cetera, and the 3.5% leakage rate, which I hope I've convinced you is reasonable, the red now is the methane component of that. And you still see that heat pumps are the way to go, but it actually reverses it. You know, your number one priority might be to go after those natural gas heaters. And you know, in the state of New York, between 15 to 20% of our total household energy use goes for hot water. Natural gas, the primary use of natural gas in our state is in homes, and about 25 to 30% of that natural gas in homes is for these hot water heaters. So the sort of tanks I'm talking about over here, you can buy from Home Depot for $1,100, $1,200, and that makes a huge difference at the state. So that's it. My take-home message is that shale gas is not good. I hope I've convinced you of that. And I want to take a break and then handle questions. Who wants to handle things here? I'm happy to talk, but you've been sitting a long time.
By dint of refusing to accept the notion of life cycle emissions and their impact on the impact of methane over 20 years as opposed to 100 years, have been quite happy to approve fossil fuel-driven projects that will last for another 40, 50, 60 years. My message, therefore, is one, bad on them, but two, we, the citizenry, as we become educated about that, have to be vigilant and vociferous about saying, no, that's not acceptable. Mm-hmm. So I say in conclusion, good on folks like Extinction Rebellion and good on Sunrise the Kids. Whether they're sophisticated about this or not, they have to disrupt business as usual, or we'll just go down the hill or up the chute, whichever one you choose.
You know, I totally agree with you, and I say I'm proud that Cornell and Tompkins County both sort of adopted this approach in 2016, but in both cases they've backed off of it to various extents and in various ways, and so I think we need to push them hard on it. At Cornell, the provost has set up a new committee to think it all through again. I'm on it. Others in the room are on it. I'm cautiously optimistic that we will see reason before the academic year is out. And I think the fact that the state is adopting this, it will be state law. And any decision that the state makes, licensing decisions for pipelines, et cetera, have got to take this into account. And I think that's a fundamental change. Now, just because it's state law, it doesn't mean that it's binding on the county or Ithaca or even Cornell necessarily, but I would hope that it would set an example and that our local governments, from which this idea came, I mean, it came from Cornell and Tompkins County to the state. It'd be nice to have the local communities in my institution adopt it back. And in the case of Cornell, I think it actually might be legally binding, because although Cornell can account for its greenhouse gases in any way it likes for its self-reporting, when we borrow money from the New York State Dorm Authority to build buildings, the Dorm Authority, as of January 1, will be required by this new law to use this sort of accounting in determining any impact.
Any other questions? The lady in the back. Stand up and give your name.
Well, you didn't talk about it, Bob. I think there's another reason to be concerned about methane, and that is because it's such a potent ozone depleter. Mm-hmm. And could you explain a little bit about that? Does it matter which isotope of carbon is up there, but it's a short residence time that is like 100 or 400 times more lethal to ozone because it knocks out the oxygen atoms? But I mean, another reason, if emissions are going up, another reason to be concerned, because I thought we were making headway on the ozone depleting gases.
Yeah, there are a bunch of things going on there. The carbon isotopic composition of the methane doesn't really matter. Its basic chemistry would be the same. So what the isotopic chemistry does is give us a tracer so we can look in some ways at what's going on, but the chemistry is the same. And ozone's complicated because there's ground level ozone in our room and on our city streets, and there's ozone up in the stratosphere. And the stratosphere, we want it because it cuts down on UV radiation that's hitting the Earth's surface. Down here we don't, because it gives us emphysema and damages our lungs and causes premature death. And crop yields are about 15-20% lower in the United States than they would be if we didn't have as much ozone. So it's a real financial burden. Methane contributes to the formation of ozone at the ground level. It's a major contributor to it, so that's a big problem. In terms of what's going on in the stratosphere, it's a little bit more complicated. The methane that we release to the atmosphere, most of the final sink is oxidation in the stratosphere. So it's oxidized to carbon dioxide and water vapor. The methane itself isn't really doing anything to ozone in the stratosphere, but it's a major source of water vapor to the stratosphere when it's oxidized. And the water vapor in the stratosphere does make a difference to the ozone up there. But the chemistry gets really complicated really quickly. It's one more reason not to be increasing methane now.
Another question in the room? Yes?
Hey, Bob, Sandra Steinberg. Could you show us that slide again of social costs? And my question about it is, has anyone monetized the cost of transforming our energy and home heating and water system in such a way that we could compare the $60 billion a year from using oil and gas versus how much it would cost to transform everything away from coal and gas?
Not that I'm aware of. It's a great question. Again, Drew Schindel has published on this. This particular one assumes a 4% economic discounting. It looks even worse if you use different discounting rates. And again, this is from that ground level ozone primarily is the concern there. So it's a real health cost. It's a real agricultural cost.
So that includes health and agriculture costs as well? And that's
Yes, it does. It's primarily health and agriculture. And it's, I think it's about 2/3 health and 1/3 agriculture. The climate change costs of that are small relative to it. So it's an ozone health and biological damages issue, which does not get enough attention.
Well, we have time for another question right here. Stand up and give your name.
My name's Stephanie Redmond. I'm wondering if you see any hope in the modern technology that's coming out for carbon sequestering and methane sequestering.
No. Yeah. No, I'm not a big fan of sequestering. The way to keep methane out of the atmosphere is to not take it out of the ground, to leave it where it is. And the same for carbon dioxide. So where I'm very optimistic is on the technologies of solar and wind and hydro. Mark Jacobson and I published a paper, and others published a paper back in 2013 laying out a blueprint whereby the state of New York could be completely fossil fuel free in about a 15-year time period using technologies which were available. That's now 7 years old. Prices have gotten better and better and better. We're on the trajectory to make the transition. Governments could do more to make it happen faster. I think the storage technologies are all there. Be delighted to talk to people further about that, but I'm very optimistic that we can get rid of fossil fuels. Once we use them, the technology, there is no proven economically effective way to pull CO2 out of the atmosphere. Methane's harder yet. So let's not put them into the atmosphere. I think that's the real solution.
Another question right here. Stand up.
Yeah, so I'm Dan Kogan. I'm currently the Chief of Staff for the City of Ithaca. And I want to preface this question because I imagine some people are going to think that I'm trying to get the city to not take a certain action. And this is really literally a question about implications. And so I know there's a big push to electrify, our energy systems, and I certainly have been supportive of that. But when I start to think about that, first of all, there's the global warming potential of refrigerants, and I know you showed that graph earlier that showed that it was mostly carbon dioxide and methane. But I do wonder, has there been any research on if we were moving towards a complete electrification of our grid, how much would refrigerants play a role in that? That's one question. And the second is the amount of BTUs that come into a community through a gas pipeline is considerable. And so what would we have to do to our electric grid in order to allow that much energy, or maybe hopefully a lesser amount of energy, come into a community? And what are some of the implications there?
Yeah, those are both great questions. On the refrigerants, many of them are greenhouse gases, some are not. And so, we really should think carefully about what we're using as we scale this up, and that has not gotten sufficient attention. So I agree with you. We should be thinking about that. In terms of what it means in terms of the energy transition and delivery of energy to Ithaca and similar communities, if we switch, say, to using ground source heat pumps, the efficiencies of the pumps are in the neighborhood of 400%, give or take a little bit. You're extracting heat from the environment, so it's more than 100% efficiency, which means that the overall energy use goes down, although, of course, the electric use goes up. So for the state of New York, we did the calculation as a whole in the Jacobson et al. Plan, and the electricity production statewide would basically need to double if we're to electrify all heat and transportation. Energy use for the state goes down by about half. So both things. So yes, we do need to deliver more electricity. We need to be thinking about that, and we need to have the grid which will support it. But that's all doable. Those are relatively small technical challenges. And we need to do it. That is the way to address global warming. I'm convinced 100%.
Here, stand, give your name.
Dean Nicholson, I just wanted to say, if you want to learn about green refrigerants, two of our students from our Climate Challenge put a keepitcooltompkins.org website together, which educates you on refrigerants and the green alternatives that are coming along. And EPA has a green chill program, so it's important that as we push for heat pumps in our cars and everywhere else, that we also get the automotive industry and everybody moving towards these other kinds of refrigerants. And I did have one just little data question.
Yeah.
The graph of the increase in methane since 1980, and then it flattens around 2000. What was all that increase about?
Back in the 20th century?
You know, 1980 to 2000.
It was going up. Yeah, we don't entirely know, and people argue about that, but the general consensus was that was increase from fossil fuel emissions. It's consistent with that, and as to what caused it to level off, people debate a lot, and the data are sparse. We're getting better at making these measurements. We're getting better and better now as we get satellites up there, so you have to hand wave it. But my personal belief, and it's consistent with the science but not proven, is that the 20th century increase was largely from oil and gas industry, a lot of that in Russia and Kazakhstan and Iran, and that the increase in the 20th century, German engineers went in and rebuilt the pipeline systems into Siberia at that point in time. So I think that's what happened, but you can't prove it with the data that are on hand.
I think we can wrap it up now. Thank you, Professor.
Okay. Thank you. Thank you for coming. Have a good holiday.
If anyone...
This is not a closing remark, it's just one last little fun fact about refrigerants. Cornell is the highest user of refrigerants on the American East Coast between their Ithaca campus and the New York State
Well, Ruben drives a train from downtown to Spain. Hear that whistle blow 100 miles. Oh,